Good evening, dear students. Our current lecture is the remaining part or in the continuation of the previous lecture, gravitational potential due to a spherical shell or a hollow sphere. Dear student, we had three cases. The first one was when the point P is lying outside the spherical shell, which we had discussed earlier. The second case was when this point P lies on the surface of the shell, which we had already discussed just by a mere replacement of lowercase r with the uppercase r. And now the present case is when this point P is lying inside the spherical shell. So let's discuss this third case. Dear student, we will continue from this expression where we had converted two variables into a single one. This was our expression for gravitational potential due to this ring. And dear student, we did integration for calculating the potential due to this whole spherical shell, and the limit of integration was from this point to this point. So there is no major difference between this case and the previous one. The only thing which we have to change is the limits of our integration. So dear students, let's see here dv is this one, and if this point is lying say at this, we had selected arbitrarily that this point is lying at this point. So its radius, I have to erase this. So this is point P instead of this. Now for calculating or for doing integration, we have to consider this distance from point P to that one. And dear student, r was the distance from the point P to the center of the cell. In this case, this one is our r, lowercase r. So this is r. Now this disk can be, or this disk is started from this point and end up at this point. So our limit of integration for this, v is equal to minus 2 pi r rho g by r integral dx. Now dear student, the first disk start from this distance. So this distance is, dear student, this complete distance is radius of the spherical shell, which is r, and this one is our lowercase r. So let this point is say q, this one is a q, then pq here is r minus r. So our first disk which we have to consider for calculating the gravitational potential lies at r minus r distance from this point P, and the last disk will lie at this point. And dear student, from P to this point, say this is S, PS is this one plus this one. This one is our uppercase r, which is the radius of this spherical shell, and this is lowercase r. So r plus r. Now dear student, we have to integrate this from r minus r to r plus r. As we advance it further, v equals minus 2 pi r rho g by r x r minus r plus r. Now substituting our limits of integration, we got upper limit which is r plus r minus the lower limit, which change the sign of both r. Dear student, this becomes 2r, and v equals to minus 4 pi r lowercase r rho g by r, and this r is again gets cancelled out, minus 4 pi r rho g. This is the potential. Now dear student, multiply and divide this equation by uppercase R. So we got this one. Now 4 pi r square is the area of the cell multiplied with this rho. Rho is mass per unit area. So this quantity gives us the total mass of this cell, and is this finally becomes gm by r. And dear student, for our surprise, what we have found out, it's a constant quantity minus gm by r. All these three factors are constant for a given cell. And dear student, if we recall the previous case, when this point P was lying on this surface, at this surface V comes out to be minus gm by r. So the potential, gravitational potential at this point is equal to gravitational potential at this point or any arbitrary point which is lying inside the cell. So we can say that gravitational potential inside the cell is a constant quantity, and its value is same which is at the surface of the cell. And dear student, if this is a constant quantity, and if we derive formula for gravitational field strength I by using the relation minus dV by dr equals I, you get 0 because this is a constant quantity. So here gravitational field strength is 0 inside this cell and proportional to minus r square outside the cell. But gravitational potential, it's a constant quantity. So whatever the case, if the point is lying on the surface or lying anywhere in the cell, you got the same gravitational potential. And if we represent it graphically, then we have to draw this graph in the fourth quadrant, because we had negative gravitational potential for positive r. So this condition is fulfilled only in the fourth quadrant. Say this is our this axis representing our gravitational potential, which is a negative quantity for all these three cases. And dear student, this is a r, which is a positive quantity. So what we have observed, that at the center of this cell, our gravitational potential is minus gm by r, which is not 0. So this is say minus gm by r. Okay, and this potential, this value is also for this. So means as we move from O to Q, at every point gravitational potential is constant, which is minus gm by r. So up to lowercase r is equal to uppercase r. This has a constant value. So this is our r. At this point r equals uppercase r. And dear student, when r less than r, it's constant, and when r greater than r, its value was, as you know, if the point was lying outside, then it was minus gm by r, or we can say our v was inversely proportional to r. And we can say as we increase r, if we increase this r, the overall value for this ratio will decrease, and if negative sign is multiplied with this, or we can say there is negative sign, so if this quantity is decreases, means v is increases. And for r equals, as r tends to infinity, our v tends to 0. So dear student, its behavior will be inversely proportional to 1 upon r. So this will be the graph v proportional 1 by r. And dear student, you can see you do not need to touch this graph with this axis, because it is going to touch when r is infinite. So this is the graphical relation, and I have seen that this graph is quite important for your competitive point of competitive exam point of view, and also important for your university exams. Thanks for watching the video, Parvich.